final talk of the afternoon session from Maissa, Salama in UC Santa Cruz, talking about exoplanet imaging with large segment telescopes.
All right. Hello, thanks everyone for being here. I'm Maissa Salama, I'm a postdoc at UC Santa Cruz, and I'll be talking about using Keck as a test bed for next generation telescopes, in particular for exoplanet imaging with large segmented telescopes. And so before diving into it, I want to highlight that there are many people involved in this project from UC Santa Cruz, Caltech, Keck, JPL, LAM, and Space Telescope. And here's a cool video of our Zernike image of the Keck primary mirror as we were poking each of the segments. All right, so as we all know, one of the big goals in astronomy for the next decades is to directly image rocky planets in the habitable zone of their host stars. So from the ground, with the ELTs, we'll be aiming for planets around low-mass stars. And to directly image an Earth-like planet around a Sun-like star, we'll have to go to space. And that'll be the goal of the Habitable Worlds Observatory, NASA's next flagship mission. So as we all know, the next generation of both space missions and ground-based telescopes will all have segmented mirrors. And Keck is currently the only segmented mirror telescope with adaptive optics and high-contrast imaging instruments. So it's an ideal test bed to test these different segment co-phasing technologies. So just to highlight the impact of these segment-to-segment co-phasing aberrations, they introduce these mid-spatial scale aberrations that are particularly damaging to contrast. So here's a perfect PSF for a Keck-like aperture, and then when you introduce segment co-phasing errors, you see how all the speckles get blurred. And so the scattered light is light that's not suppressed by the coronagraph. So our goal is to use Keck as a testbed for HWO. So current state-of-the-art testbeds can't take into account the full effects of a full-sized telescope with realistic segmented mirrors that are non-flat. And so although obviously on the ground we're not going to reach down to the picometer level that will be required for HWO, our goal is to test the whole system level. And so Keck is the only facility that has all of the subsystems that are necessary for testing these segment co-phasing technologies. In particular, a segmented primary mirror with capacitive edge sensors, a deformable mirror, a Zernike wavefront sensor, and high-contrast science instruments so that we can directly measure the impact on real science data. All right, so we heard about the Zernike wavefront sensor a couple times earlier today. So just to go over how it works, it uses the phase contrast technique that was originally developed by Fritz Zernike for microscopy, for which he got the Nobel Prize. And so the way it works is that it converts phase variations into intensity measurements that we can image on a detector. So you have your light coming in from the left, bring it to a focus, and we place the Zernike mask at focus. There's a dimple on the mask, and the diameter of that dimple typically matches the size of the core of your PSF, which imposes a phase offset to the core of your PSF. And from that, you create a reference wavefront, which interferes with the rest of your light, and from that interference pattern, you recover the phase information. But the main thing to remember about the Zernike wavefront sensor is that it's very sensitive. We saw earlier it's one of the most sensitive wavefront sensors, which also means it has limited dynamic range. It's been shown in temperature-stabilized lab environments to reach down to the picometer level. And it's also sensitive to phase discontinuities, which is not the case for the more commonly used wavefront sensors like the Scheck-Hartmann or modulated pyramid, which measure the slope of your wavefront. So it's really ideal for these segment phasing tests. So here's our setup at Keck. Because the Zernike wavefront sensor is so sensitive, it has to be downstream from the main AO system because you need an already decent PSF to work with. So we have the main Keck AO system, which has a visible Scheck-Hartmann wavefront sensor. The infrared light is then sent to the NERC2 science camera, And the near-infrared light is sent to Keck, the Keck Planet Imager and Characterizer, which we also heard about a couple days ago. So here, I stripped it down just to the relevant components for the Zernike wavefront sensor, which include a deformable mirror, which we use to correct for non-common path aberrations, and a tip-tilt mirror to keep the PSF well-centered on the Zernike mask. Now, the Zernike mask itself is actually a vector Zernike mask, and so it's made of a metasurface material, which allows us to basically combine two masks in one. So we can impose simultaneously two different phase shifts to the X and Y polarized light. And these masks are designed and fabricated at JPL, and Kent Wallace is also here at this conference. And so we have the Zernike mask, then we have a Wollaston prism to split the two polarizations. And so we have our two Zernike images, which allows us to extend the dynamic range. It basically doubles it. All right, so we first demonstrated controlling the primary mirror segments using the Zernike wavefront sensor in closed loop. So here are some of those results. Here are the before and after Zernike images, the before and after piston measurements, and the before and after PSF images on the NERC2 science camera. So here by eye, you can see the improvement in the PSF. So we've done this many times since. And here's a plot showing our improvement in Strel ratio as a function of the starting Strel ratio. So generally, we improve the Strel ratio by about 5 to 10%. But you can see that there's a range of performances and a range of starting conditions. And so we're interested in understanding everything that goes into the different performances. So during each of our runs, we collect a lot of data. We have our performance metrics, so our measurements of the segment pistons from the Zernike, our Strel ratios on the science camera, as well as contrast measurements, which is what we ultimately care about. We also collect telescope and AO information, so the telescope elevation, the sky parallactic angle, and AO telemetry, so the DM commands and Shack-Hartman slopes, and the environmental conditions, so the seeing throughout the night, wind speed, relative humidity, and various temperature sensors that are placed near the primary mirror, secondary mirror, inside, outside the dome, to really try to track everything that's changing throughout our runs to understand what impacts the performance and our measurements. And so for the analysis, what we want to do is to isolate the impact of segment cophasing on science performance. And we need to do that to better understand the environment and the system so that we can draw the relevant conclusions for HWO and separate effects that are specific to Keck or ground-based. So what we want to do is determine the optimal phasing technique. Generally, what we have in mind when we think about segment phasing are segments that we want to align. But in reality, the segments aren't perfectly flat. And so determining the best way to align these segments is not trivial. So the way that it's currently done at Keck is with the phasing camera system, which minimizes edge discontinuity. So they align to segment edges. The Zernike wavefront sensor, on the other hand, aligns to the average phase over each segment. And since the segments aren't perfectly flat, these two things aren't exactly equivalent. And so what we care about is understanding what leads to the best AO image quality and the highest contrasts. So we've taken some contrast measurements to do this comparison. So here are some first results. We have a few more, but still analyzing the data. So here are the contrasts in the nominal state of the primary mirror. And then here are the contrasts after running our Zernike closed loop. So to make things easier to see, here's the ratio of the nominal and Zernike contrasts. And so in general, we see an improvement by a factor of about 1.5 to 2. And when we take these contrast measurements, we want to make sure to match equal sky rotation and equal integration time. So we look at the same target and we alternate shapes on the primary mirror as the target rises and as it sets, so that it's a fair comparison. Now, from our Zernike images, as you can see, we see a lot more detail than just segment cophasing information. And so generally, for our wavefront sensing and control objectives, what we want to do is to develop dual mirror control. So we want to determine the optimal wavefront control strategy, controlling both the primary mirror and the DM with the Zernike wavefront sensor. So just to illustrate this, we want to go from our Zernike images to our reconstructed phase, and then we want to separate what originates at the primary mirror, correct that at the primary mirror, from other aberrations and correct those with the DM. Then we also want to fold in the edge sensor data so that we implement dual mirror, dual sensor control. And we want to do all of that in parallel with high contrast science observations so that we can directly measure the impact on the science. So to begin doing that, we did a first test where we applied some known offsets on the primary mirror, because to do this, we want to be able to disentangle the sources of aberrations. So here for this test, we applied piston offsets in a trefoil shape on the primary mirror. And we can see on the NERC2 science camera that we see the trefoil shape in our PSF. So that confirms that the AO system is not sensing the segment piston offsets that we were putting in. We run our Zernike closed loop, and we can see that we did a good job of removing this trefoil shape. And when we compare the inputs and the correction, we have a residual of about 37 nanometers RMS. So the AO system is really not sensing these piston offsets. Then we did another test the other way around. This time we put a trefoil shape on the DM. As I said earlier, we collect DM telemetry. So here we can see the trefoil shape in our DM telemetry. We see the trefoil shape on our NERC2 science camera. And then we run our Zernike closed loop as if we didn't know where the aberrations were originating from. And we control the primary mirror segments. And here we can see on the pattern, we see a trefoil shape on the primary mirror piston offsets. And we see that it actually did a good job of removing the trefoil. It's a low order mode, so, but still. And our final test for disentangling these aberrations is to do a rotation test. So we have the data, but still analyzing it. So hopefully at a future conference, I'll show it. But basically, what we want to do is to make sure that we understand what the AO system is doing upstream of the Zernike wavefront sensor so that we can interpret our Zernike measurements in the best way to implement this dual mirror control in the most effective way. All right, so just to summarize, we're using Keck as a test bed for HWO to validate segment co-phasing architecture techniques. We've set the stage by demonstrating the closed loop control of the primary mirror and improving the science image quality. And we're working towards this dual mirror control and dual sensor, doing all of this in parallel with high contrast observations. And this will be the first time that these complex nested co-phasing architectures that use different mirrors and sensor technologies will be tested on a segmented telescope. All right, thank you.
Hi, great talk. Sam Walker from University of Hawaii. I was just wondering how fast you're able to do this, if this is something that you're wanting to do on Sky.
Yeah, great. I forgot to mention that. That's a good question. So we average over AO residuals. So typically we take about 30-second images. So it's a slow closed loop. But we can run faster, and we've done some tests where we ran at 600 hertz on a very bright star, stars that have names, and to look for vibrations in the system. And we just did that test a couple weeks ago, so yeah.
Hey, great talk. I was just curious, you guys have edge sensors, but HAB worlds might also have other different types of metrology. Do you think there will be avenues moving forward to, test those new types on Keck and install different types of sensors?
Yeah, so there's been talk about thinking about laser metrology and seeing how that could be implemented on Keck. So that would definitely be a possibility. Yeah.
Maissa, great talk. I had a question about some of the numbers you showed in terms of improvement. You mentioned the strawl went from 50% to 60% when you closed the loop on wavefront sensing. what was the predicted improvement? Was that better or worse than you expected? And similarly for the second set of experiments you showed, like, is there a quantitative way of saying it figured out the amount of trefoil that we put on the DM with the correction that we found on the primary, or?
Yeah, so for the expected performance, so at Keck, there's the Keck AO error budget, and there's 3 leading terms, and one of those is the margin error, where many people think that the segment co-phasing errors are part of this margin error. But that's one thing that we're trying to figure out with the Zernike wavefront sensor. So it's about 130 nanometers RMS in that margin error. And it kind of matches when we do our closed loops. It ranges, but it's around 100-ish nanometers RMS that we apply. But what we think is happening is we're probably measuring more than just the segment co-phasing errors, but just applying them in our correction on the primary mirror. So that's why we really want to try to disentangle where these aberrations come from. But that number, we're trying to figure it out. Yeah.
Let's thank Maissa again. Okay, that was the last talk of the session, but I think the meeting